2.1 is all about displaying and describing categorical data. As a reminder, categorical data is data that divides us into categories or describes a quality. So an example of a categorical variable would be one that we collected last Tuesday. Did you set an alarm when we were trying to figure out who woke up first on Sunday? So did you set an alarm? Simple binary categorical variable, we're going to have yeses and nos. If we were collecting data like my first class, you'd have a bunch of terrible little slips of paper that all had people's responses on them, right? And then if you were collecting like we did in the second two classes, you would have been writing all down everybody's responses as they came up. But you probably, if you were only collecting this variable, would have stopped that really quickly and had just kept a tally instead. So you would have just counted up everyone who said yes and everyone who said no, keeping track. Even if you had these piles, you're making a pile of yeses and a pile of nos. This is really getting down to what we call a frequency table. We had 5 yeses and 3 nos, right? So that's one way to look at this data really quickly, really easily. Instead of having a giant pile of data, we now know how many yeses, how many nos, how many males, how many females, whatever our particular categorical variable might be. Another thing we can do is look at a relative frequency table. So a relative frequency table, instead of looking at the counts, it looks at the proportions or percents, or, proportion being the decimal version. So you may have instead 0.625 and 0.375, because 62.5% of the answers here are yes, and 37.5% are no. So this is just one way to summarize categorical data. If you want something a little bit more fun, using that word very loosely here, you can make a display. And we have 2 different displays that both arise directly from this frequency table. One is a bar chart. So all we're going to do is turn those frequencies into bars, as we saw a lot of people do in class today. And the other is a pie chart. Only thing I'm going to mention here, I'm not going to talk too much about them because we all know what they are, is that a pie chart can only be used when each of the answers is mutually exclusive from the other. So you can imagine if you're setting up a survey, it's like you have to be like a choose one type of a deal versus a choose all that apply. You can't have one of those like choose any race that you identify with. You would need to say choose that which you most strongly identify with or something, so that everything is 100%. So in order to give us a little more interesting stuff here, we're going to talk about possible problems that can happen with categorical graphs. So I have 2 very silly examples here, but they both illustrate an issue that happens in real life. So first one, we see Halloween candy collected, and we got Shayna and Michael. First thing we think, we don't even look at anything axes-wise, is that, holy crap, Michael took away a ton more candy than Shayna. And if I asked you how many times more candy, think about it for a minute without looking too hard at it, you'd probably say about 4 times as much candy, right? Looks like he brought a freaking pillowcase and she has one of those little plastic pumpkins. But if we actually dive into what the numbers are here, we can see it looks like the number of pieces that Michael got are 36, and the number of pieces that Shayna got looks like it's about 18. It's only a difference of 2, right? It's only twice as much. So what's the big problem? The big problem is that if these were bars, it would be very obvious that Michael got twice as much candy, roughly, compared to Shayna. But since they use this crazy candy corn, the candy corn looks more than twice as big, and it is more than twice as big. This here violates, I keep doing that, violates the area principle. The idea being that the area taken up by something in one of these graphs has to actually be proportional to the amount that they represent, right, compared to the total. So you can look and say, okay, I don't have to look too hard to see, in this particular example, coal is the biggest piece. And it is more than, it's almost twice as big, if not a little bit more than this other group, this blue section, right? I don't have to look very hard at the graph to know these things because I can visually see what it does. Whereas here we're violating that problem. The second one, here's bowling averages, has the exact same problem. First glance, Emily looks like she's 3 times a better bowler, got a score 3 times higher than Hildy, and Diana had a score that was twice as good as Hildy. But then when we dive into the actual numbers of this, Emily's score looks like it was a 126, Diana's was a 120, and Hildy's was about a 114. And I'm just making guesses here, but turns out these women all scored very, very similar bowling scores, which is not what this is telling us at all. It also violates the area principle. It violates it for a different reason. Instead of using a cutesy candy corn, which, by the way, this is something we do need to be very much on the lookout in the day and age of infographics. Everybody is taking their statistics, like, make this fun and nice, and they give it to a graphic designer who puts a candy corn in there, and now it violates the area principle, and it's not telling the right story. But this is something you see a lot. It's a truncated axis. So our truncated axis, if we actually kept this axis going down, I tried to measure it out really briefly. If we actually kept this axis going down, we would need to come about this far down before we get to where 0 would be. So you can imagine if these bars were that much longer. Now it looks like these women are all pretty similar, right? As opposed to seeing these huge differences we saw when it was violating the area principle. A last thing I want to do is just briefly bring up 2 examples of this in the news. They are slightly outdated, but I do think it's important. First one here is this little graphic of gun deaths in Florida. So I'm going to go ahead and grab it so I can sketch on it. This gun deaths in Florida, I'm hoping it's still recording me. Hold on a second. I'm scared, so I'm going to exit. All right, I don't know. I'm not going to use it because I'm scared now. But I'm going to talk about it, and hopefully you can just follow my little cursor. So first glance of this appears that the number of murders committed using firearms after 2005, when Florida enacted Stand Your Ground law, looked like it went down. It has a huge dramatic decrease once Florida did that, right? But if we dive into these numbers, we actually look and see, okay, well, back in 1990s, there were 873 number of murders, okay. And then there was somehow, this is higher, but the numbers went down. And then we glance at this axis and see that they just inverted the whole axis. This whole thing should just be flipped upside down. Turns out once they enacted that Stand Your Ground law, the number of gun deaths went up and then up again and took a big spike, right? So this is an example of somebody manipulating a graph in a way that's probably trying to tell a different story than they meant to. Another example, I'm not going to do any more after this. I'll give you guys links, so if you want to see more, you can. This one shows a Fox News graph with Obamacare enrollment as of March 27th, and then their goal for the 31st. 7 million to 6 million. And you can see even here in this title, 5 times, that's the area of this. It's almost 5 times more, as large as this. I think it looks like 3 times. I think, you know, BuzzFeed is getting a little liberal with that amount there, a little alternative facty on that amount. But it looks like it's almost 3 times as much. Like, we've only gotten 1/3 of the enrollment necessary, when in reality, they're missing 1/6 of the enrollment, or 1/7 of the enrollment that they wanted. So we need to bring these down. Again, we have those truncated axes that are causing a problem. So this is something that happens all the time. People want to truncate axes either to change the story of what you're seeing and make it appear worse than it is or appear better than it is, or that they just don't realize that that's not a good thing to do. So with that, I'll leave you, and we'll pick up again in the next video with 2.2.